do that is we use big numbers called coefficients. So let me get out the magnets here. I'm not going to spend a lot of time on this, maybe just this one example, and then we're going to move on. But when we balance equations, that's what we're doing, is showing the law of conservation of mass. So let's say that's our hydrogen. So I need 2 of those there. And we'll use yellow for the oxygen. All right, so there's H2O2. Actually, it looks like that. And then you got water here, and you got oxygen there. Okay, so what I'm trying to show you here is that the number of particles on both sides, so my reacting particles and my product particles, need to be equal. That's the only way mass can be conserved. Okay? So that Regents question we did, if I have 10 grams on this side, I need 10 grams on this side. If I have 1,000 grams over here, I need 1,000 grams over here. That's a little bit easier, I think, than this concept, but it's all the same thing. How many red do I have here? 2. How many over there? Red's balanced. How many yellow? 2. How many yellow? 3. Not balanced. So what we're going to do is we're going to use coefficients. So we're going to put like a big 2 here, or a big 3 here, or a big 4 there. I'm just showing you as an example. So when I do that, if I was to put a 2 in front of here, then that would mean I have 2 of those. So let's do that. Let's take 2 H2O2s. All right? So now, what's not balanced? The red and the yellow. Right? So what could we do next? Add another water. So we can add another one of these. So is the red balanced? Is the yellow balanced? Is the whole thing balanced? So again, think of this arrow as like the middle of scales, right? So you got scales that need to be balanced. Balance is a good word because that's what this is called. Balance means conservation of mass. So go ahead and throw 2 2's there, one in front of H2O2, one in front of the water. And really, again, what I'm trying to stress, mass can't be created or destroyed, just transferred. So the mass of the reactants are completely transferred to the mass of products. In real life, this is really hard to prove. All right, I did the little demo on the scale where we, who pinched it? Was it you? No? So, she pinched it and it reacted, it turned white. So obviously something happened, but the mass on the scale didn't change. So that's the best way I can show you a visual of this. The number of particles will always be equal on both sides. Okay, but again, in real life it's really hard to prove it, but on paper, this is how we do it. All right? So I'm just going to leave this alone now. We're going to move on. We've kind of been talking about conservation of mass and energy, probably a little more than I usually do, but it's an important concept. All right, so we will come back to this down the road. All right. So don't forget, we have that test on Wednesday. All right? So it's only a couple days away. Everyone has a review sheet for that?
No.
Good thing I asked. Did I hand these out yet?
No.
Oh, crap. You want to take it on Thursday?
Yeah.
Let's do it Thursday. Thursday's a good day for a quiz, test. It is a test, kind of a big test, your first test. So give you another day to kind of get ready for that. All right, so I'll change that. All right, so this is typically how my review sheets work. Most of it is just going to tell you what you need to know. Okay, you need to know properties of metals and nonmetals. You need to know the definition of element compound. I'm not going to read it all to you, but then sometimes on here I have questions. You know, like number 18 is a question. This one tends to be, this little sheet tends to be, do I have anything on the back? No. Mostly just, this is what you need to know. Sometimes I'll have more like practice problems. So if you want to, you know, review after school or something, let me know sometime between now and Thursday. But yeah, I would definitely, the best way that I would suggest using this is maybe just kind of write all the things down on separate paper or on the back, right? So properties of metals. Go to your notes, go to the book, internet, whatever. Probably your notes is the best spot. Say, okay, what are properties of metals and nonmetals? And maybe literally rewrite them. I don't know if that's going to help you, but it might. Define an element, write it down. So that's like one way you can actually physically study. Kids sometimes have a hard time, like they don't know how to study. You know, and if I just say, read through your notes, that's just kind of something teachers say sometimes, and kids do it or don't do it, I don't know, and it doesn't help too much. So this is something you can actually do. Like I can read this, look it up, maybe even rewrite it, and that'll help you remember what you need to remember. So there will be mostly multiple choice, but some short answer. I have it right over here. It is, yeah, 34 questions. 1, 2, 3, 4. Oh, I'm sorry. No, 38 questions. So 1, 2, 3, 4, 5, 6, 7, 8 short answer. So 30 multiple choice, 8 short answer. I don't know. I feel like maybe I should do like a short answer on Friday, just because I don't know if we're all gonna have enough time to do all those in one period. So. At any point, you might have just multiple choice on Thursday, maybe short answer Friday, but you're going to have your test on Thursday. All right. So, there's that. I'm glad I asked that question. Sorry, I forgot to give that to you. All right, questions for me? Anything you're concerned about here before we move on? Okay. Moving on, new stuff. You guys ever seen a vacuum chamber? Not a vacuum like you clean the floors with. When I say vacuum chamber, what does that mean to you guys?
That's perfect.
A what?
That's perfect.
You sure?
I'm just thinking.
If I say, you know, the word vacuum in a science class, what does that mean? A vacuum. Space is basically a vacuum, not totally, but. So what's a vacuum? Did you say space? A void. Good. What's that mean? Just what? Like a black hole. Now we're getting crazy talking about black holes.
That's what I thought. You said vacuum and you said space.
I don't know, it's
All right.
just all this space that's not.
Okay, a vacuum technically is a void. That's a good word with no air particles, or no particles at all, which is kind of confusing. So I'm going to show you this animation, and I'm going to challenge you to figure this out. Okay, here we go. Lights, please. So we're getting into, here, you can title your notes, gases. And there's 3 gas laws we're going to learn right now, and it explains how gases behave. So first thing I'm going to do is actually, all right, yeah. I'm going to kind of change up on this. Change up my plan. I'm going to show you a video of gas particles, of a sample of a gas, in a container, in a box. And all I want you to do is write down 3 things you observe. That's not it. You're writing 3 things. So in your notes, write gas in motion. You're writing 3 things that you observe. At least 2. Give me at least 2, but there is a third one. The problem is, all right, you know what? I'm going to show you another animation too, because this one doesn't do everything I need it to do, but it's a good visual. Give me 2. 2 observations of how these gas particles are moving. 8 crazy alarm clocks that are sure to wake you up. That's the kind of stuff, and YouTube is a giant waste of time for the most part. Sorry, guys. What kids do before YouTube? Okay, 2 observations of how gas particles move. Okay, I'm going to show you another animation. Oh, and with this whole hot pack thing, raise your hand if you could tell me the transfer of energy from where to where. You can raise your hand if you can. I wanted to talk about it and I forgot. Like a Regis question would say, you're holding a hot pack. Explain the energy transfer. Raise your hand if you could do that. Everyone should be raising their hand. Emma, go ahead.
It's going from the hot pack.
From hot pack to your hand. Why? Don't say hot to not.
Because the hot pack has more energy.
Good. I'm not gonna let you off the hook yet. Use the word temperature in your answer.
Oh yeah. Okay. The hot pack has a higher temperature than the temperature of the hand.
Perfect. Which means your hand has less energy and the hot pack has more energy. Good job. All right. Sorry, that was a little random there, but I wanted to talk about that. Okay. This is a cool, cool thing here. All right. You want heavy or light?
Heavy.
Heavy. A lot of gas or a little bit of gas?
Little.
Just a little?
Yeah.
Okay. All right. Now,
That's so funny looking.
it's awesome looking. This is awesome. All right, ready? I'm gonna heat it up now. Oh yeah. This. Okay, these particles are doing something the other particles didn't. Try and pick up on that. Okay. Now I'm gonna heat it up. Watch the temperature gauge go up. Notice the pressure starting to change a little. All right. Our little scuba diver here is struggling. Now, this is a great example. See how slow this was moving? Oh, wait.
They don't move until they're gone.
See how some of them are moving slower and some are moving faster? That's really important observation. This is probably the best animation you could ever see as far as gases are concerned. You gotta know a bunch of stuff about gases. It's an important concept here, and I get all gassed up about it.
Wow.
That was funny.
Start that on Monday morning. All right, now, raise your hand. One observation of gas particles in motion.
They're moving fast.
They move fast. Good. Someone give me another one.
They bump into each other.
Good. They collide into each other. Anybody else?
Not in order.
Oh, so a lot of chaos. What's that word?
No.
Starts with an E.
Entropy.
Entropy. Lots of entropy. Good. Okay, good. Anybody else got another one? So they move fast. Lots of entropy. They collide. Anything else? They fill their container. Anything else?
Probably doesn't relate, but they're like all the same particles.
They're all the same particles. Yeah, you know what? Let's put in the light one too. It's gonna get wild.
Do a lot of that
It's
one.
gonna get
Do a lot
wild
of
in
it.
here.
Ah!
Oh.
So what did you just learn?
What do you mean?
What did you just learn? Smaller,
Move fast.
move way, not even close, way faster. That should make sense to you. You take a really big person or a really small person and you want them to run, let's say, run in a certain direction, not necessarily race each other. Which one's going to take more energy to get going? The big person takes way more horsepower. Okay? Way more horsepower. Okay? Way more horsepower. In fact, Mr. McConnelly calculates this in physics. All right? And based on student sizes. You could have a small boy or girl, a big girl or boy, but it doesn't matter. And they run upstairs and they calculate horsepower. And the larger the student, okay, and it's not about weight or what they look like. That's not the issue. It's just the science behind it. Take me or Mr. Decker, okay? All right, he needs way more horsepower to move than I do. So the same thing applies to gas particles. The small ones, they don't need as much energy to move, okay? The big ones can move just as fast, but it's going to take a lot more energy, okay? That should make sense to you guys. So anyways, yeah, that's kind of crazy in there. Now, I'm going to reset this because it's a little too crazy to talk here. We'll go back to the heavy one here just a little bit. Okay, now, how do they move? Watch how they're actually moving. Give me a way to describe the motion of them.
Blown.
How does one particle get from one place to another? It bounces up. Okay, so watch. Look at this one. And they hits it, it collides, and it changes direction. How are they moving? How does this one go from here to here? Is it curving? How are they moving? Straight lines. First thing I want you to write down. Gas particles only move in straight lines. No curveballs here. Okay? No curveballs. Take a basketball, throw it off a wall. It'll come back to you basically in a straight line, assuming you don't put any spin on it. Okay? Most bouncy balls, most balls in general, if they bounce and you don't put any spin on them, they will bounce in straight lines. Would you agree? Now, the angle that they bounce off has a lot to do with the angle they hit the wall. Gas particles are the same way. Depending on the angle, it depends on how they bounce off. But point is, they move in straight lines. Do you think these gas particles have brains? No. Do they have any sort of idea where they're going? No, they're not living beings. So, give me a word for that. They're moving in straight lines. Randomly. Random straight lines. Write that down. They move in straight lines and they move randomly. Gas particles don't have a specific direction in mind. Ooh, I'm going to go over here. Now I'm going to go over there. I'm going to collide with that guy. That's not what they think. They can't think. They're not people. Right? They're not alive. So, they move in random straight lines. That is something you need to remember. Now, when they collide, here's the key. I need a couple demonstrations here. A couple people demonstrate. Need 2 people.
I'll be one.
All right, Reagan.
I'll be the other.
Okay. Come on over to the side or over here. I don't care where. You
Over
gotta
here.
stay together. Though. All right, now. Okay. Well, that is we could for a demonstration have you start out and just run into each
Give her-
other.
give her a
Now, but we're not
concussion.
going to do that. No, we're not going to do that. Okay. Now, I want you guys face each other. All right. Now you're going to give each other high fives, but with some energy. Okay, good. Again. Okay, does it hurt a little bit?
Yeah.
No.
One more time. Okay, good. Good job. Now, explain what you feel.
Pain.
Stinging.
Stinging. Okay, why?
Because using a
Because
lot of
the
energy.
force is getting at it and you're like,
So would it be possible if they high-fived each other and Nicole felt absolutely nothing, but Reagan felt the sting? Is that possible? No. Okay? Thanks, you can sit. Is it possible for 2 cars, let's just think demolition derby, okay? 2 cars, demolition derby, speeding towards each other. Is it possible for one car to smash into the other one, and after that collision, one car is completely totaled and the other one's completely fine? Is that possible? No, that's not possible. Okay? If I punch the wall as hard as I can, I'll probably break my knuckles.
but I have a question. Let's say you're driving a car and you run into a telephone pole.
Yeah.
The telephone pole doesn't bend.
Yes, it will.
Agree.
And something will happen to the pole. Try it.
I've watched it happen and nothing happened to the pole.
Nothing at all?
No, the car was like going 55 and it just bounced off.
Find me a video of that.
It'd be a flimsy car.
Yeah, I mean, what is it, Saturn? You guys even know what it is.
Yes, I do. But
They're
I
made,
don't
they're
know.
made of plastic. Anyways, I'm trying to get you to see something without me actually teaching you. When these gas particles collide, it's like you guys high-fiving, 2 cars colliding, me punching the wall.
They both go different directions. Like one doesn't stop. They both.
Okay, so yeah, if we watch, see those 2, they hit and then they bounced off different directions. Good. Okay. But what's the point? Why did I have you guys high-five? What's the point? Boxers. Okay, if I'm boxing somebody and they hit me in the face, it's gonna hurt. I hit them in the face, it's gonna hurt them. What's happening? Think about what we just talked about.
But energy.
More general. What is this doing when I hold it? Emma answered it. Where's the energy going? Right. Okay. So what am I trying to get you to learn here? When gas particles collide, what do?
Exchange energy.
Very good. Write that down. When this is the most important thing today. You forget everything else, just remember this, you're in a good place. Okay? When gas particles collide, they transfer energy. If Nicole and Reagan high-fived and they didn't feel anything, that means there was no energy transfer. That would be literally impossible, breaks the laws of science, okay? Even if I just do this, kind of hurts, all right? Because there's energy, the wall is giving me energy. The floor is giving you energy. And when you take physics someday, there's forces at play everywhere you move in your natural world. There's this thing called the normal force pushing up. What's the force pulling me down? Gravity. But there's another force pushing up. If that other force pushing up, so equal and opposite energy and force, if that wasn't there, what would happen to me? I would just collapse. I would be crushed. Okay? So there's always a transfer of energy or force, and that's what I'm trying to get you to understand. When these particles are colliding, they feel that energy, and there's an energy change. It's really important to remember. It's just easy analogy to slap hands, or if you were to, like boys, like middle school, grade school, they like bloody knuckles. They hate each other. It's like the dumbest game ever. You guys know what I'm talking about?
Yeah.
Played it a lot.
So dumb. So, anyways, yeah, let's see who can try and break each other's knuckles. That's cool. I'm more of a man. Anyways, it hurts because you're transferring energy. You get it. We're moving on. All right, now, here's the key, though. Is this a sealed environment, closed environment? Nothing's getting in, nothing's getting out. Here's the most important part. When they collide, yes, they transfer energy, but the overall energy of the entire system, the entire container, the overall energy of the system, what? Now, I'll help you out a little bit. If this particle is moving faster than this particle and they collide, right? So if I have a really fast moving particle and a really slow moving particle and they hit, who do you think is going to win that collision? The one that's moving faster is going to probably deliver more energy to this one. Would we agree? Okay? So if you can hold that thought.
Yeah, but
Hold on. Picture time. Okay, you got two particles, right? Let's say this one, now I'm going to give you a unit for energy, joules. Let's say this has 100 joules of energy. And for now, just watch this. You don't really need to sketch it. And this has 50. So let's say this one's moving twice as fast. It has twice the energy, so it's moving twice as fast. Assume the mass is the same, right? Assume the mass is the same. Because if you take, if you take me and, I'm trying to think of somebody, like, I don't know, professional football players, like 6'8", 300 pounds. And I run at them as fast as I can, and they're not moving, they're still going to hurt me. Okay? I'm going to bounce off, I'm in trouble. So mass is important. They have to be the same exact particle. So you have this particle and this particle identical, and this one's moving twice as fast, and they collide. Okay? They transfer energy, and then they're going to bounce off. Do we agree they're going to bounce off, kind of like in the box? Yeah, okay. Someone give me numbers here. He wants to go 75 and 75. He could be right. It could be maybe 85 and
45?
65. Okay? It could be 90 and 60 and so on. Okay? Or this one could jump up to 80 and then this one would be 70. What do these numbers always have to add up to? 150. So what's the answer? What's the last part of the notes there? The overall energy of the system stays the same. Stays the same. And then write this down underneath it. It's called an elastic collision. Elastic collision. So, when Nicole and Reagan high-fived each other, the energy of our system, known as the universe, I know that's kind of silly, but the energy of the universe doesn't change because they high-fived.
That'd be cool.
Okay? The energy of the world, the energy of the universe stays the same no matter if I hit my hands together, punch the wall, cars collide, whatever. Any sort of energy transfer in this world, okay, and just like this box, the overall energy stays the same. So this particle may have less or more energy after the collision, and this particle may have less or more, but together, the overall has not changed. You guys following me here? Does it make some sense, I hope? So what do you need to know about gas particles? They move in straight lines, they move randomly. Yes, they fill their container, lots of entropy, those are all good things. You guys are saying good things. This is the most important today. Particles collide, they transfer, but no matter how much they transfer, the overall system doesn't change. That's conservation of energy. Okay. Questions on it? Yes.
So let's say like one fast particle is gonna go and hit a slow one.
Mhm.
How come the fast particle like basically stops? Is that because it's transferring over almost?
It could. If it transfers most of its energy, then it might almost stop. Right. Okay, let me show you something else here quick, then we're gonna move on. All right, here we go. What do you call this?
Band.
Rubber band. Okay. I do that, and then I do this. What happens to it? Okay, good. Did I change it? No, it goes back to the way it was, right? What's that called? It's on the board. Elastic. I use a rubber band as an analogy. Even though there's a change happening, nothing really changes, right? The overall energy stays the same. So I like to throw that out there. It helps kids a visual of what's the word elastic all about. Okay. All right. We have 3 minutes. I'm going to use it. Stay with me. Okay. Here's what I want you to do. I was hoping to give you homework. Maybe I can. Yeah, I'm going to give you homework. Very simple worksheet. I didn't teach anything about it today. Have fun with this. It's very simple. I'll explain it really quick. So we're learning about gases now. Tomorrow I'll show you a vacuum chamber. But when we deal with gases, can anybody in the front look up here? What do you see next to that 300? K. That stands for Kelvin. You need to be able to convert from Celsius to Kelvin, Kelvin to Celsius. This worksheet's going to help you do it. Look up here, please. Right here, Kelvin equals degrees Celsius plus 273 is the equation. All right, I give you one of them, you plug it in and solve for the other. All right, so I'm going to use this to kind of teach how to use that equation. If you get them all wrong, whatever, okay? We'll learn how to do that tomorrow. All right, but anyway, stay with me. I'm going to show you one more thing. Okay, just pay attention, you don't have to write it down. Now, if I heat this gas up, okay? And I wanted to draw a graph. So stay with me. So using this animation, we're going to pick up with this tomorrow. I have temperature on the X and I have pressure on the Y. I want you to pay attention to the pressure gauge and the temperature as I heat it up. And then just have an idea of what would this graph look like. Okay? So if I add heat, see the temperature going up. Notice the particles are moving faster. Pay attention to the pressure gauge.
That's hot.
Some of those are pretty fast. Okay, what's going to happen eventually? Why does it blow up?
There's too much pressure.
Okay, so as temperature went up, 28,000 Kelvin is like crazy. That's like crazy. That's hotter than the surface of the sun. What happened to pressure? Okay, good. We'll talk more tomorrow. Do that worksheet. We'll go over it tomorrow.